So that brings us to how we can relate NMF to topic modeling. So the way that we can do topic modeling with NMF using this divergence penalty is we can first form the term frequency matrix X, where we let Xij equal the number of times that word I appears in document J. So I is just some arbitrary indexing of our vocabulary. J is an arbitrary indexing of our documents. And now we count how many times these things occur and put them in the matrix X. We then run NMF to learn this factorization W and H using the divergence penalty. And then, if we wish, as an added step, what we can do is let AK equal the sum of the kth column of the matrix W. So we take the matrix W, we sum all of its columns, and let that be AK for each column. We then divide the kth column by AK and multiply the kth row of H by AK. So if we do this, all we've done is scaled our data, but we haven't changed the product of our data WH. So also, if we think in terms of maximum likelihood and we think in terms of divergence minimization, notice that both of those penalty terms don't penalize the actual values of W and H. All they do is look at the resulting values in this matrix product. So by doing this, this additional step, we have not changed the maximum likelihood solution that we found or the minimum of this divergence, because they only depend on the product. But now we can interpret the columns of W as probability distributions on words in a vocabulary. And so we can interpret the columns of W as topics. And therefore, if we factorize a data matrix consisting of counts of numbers of occurrences of words in documents, we can view the ordering of the highly probable columns of each column of W, rows of each column of W, as a topic. And we'll see that we actually learn meaningful topics this way. And so this model can be used for topic modeling in that sense. In the next 3 slides, I also want to show 3 different algorithms, one of them being NMF, and what they learn on the same exact data. So this data consists of many images of faces that look similar to this one right here, where each one is taken and it's a grayscale image. It's put into a vector, and then we put each of the images along a column of a matrix X. So each column of X consists of different images of faces, and each row corresponds to a pixel in the original image. And then we factorize this. And so we factorize this learning 7 times 7, so about 49 different clusters or topics, if you will, something like this. And then we represent each face in how it uses those 49 different clusters. So I say clusters because the first example we look at is k-means, also called vector quantization. And so these correspond to, say, the 49 different centroids that are learned by clustering this data. And then we represent a particular image by which cluster it belongs to. So if we want to think of this as a matrix factorization, we can think of this data as being represented by taking this factor, which all are shown as images just to give interpretability, but this would be one column of W, a second column of W, and a third column, etc., of W. And so we take this factor and multiply it by the number in this element here. So this is a 7 by 7 matrix. This element is 0 times this. And we take all of these, and we have 0 times everything except for here where we have a 1 in the black square, which we multiply against this image here, and you can notice that this image is equal to this image. So that's like hard clustering. We say that we have to represent each data point by the centroid of the cluster it belongs to. And in that case, what we can say, if we want to view that as a matrix factorization, is that every data point has to be a matrix of factor loadings, like this matrix, times a vector with all zeros except for a 1 according to the cluster assignment. And we're representing all of those vectors and matrices in this way just for visualization. And so with k-means clustering, we have a hard clustering assignment, so that means all zeros except for 1 according to the cluster it belongs to. Now let's look at SVD. If we took exactly the same data matrix of columns of faces, and we did SVD, and we looked at the singular vectors, the left singular vectors shown as an image, we would get something like this. So remember, the singular vectors all have to be orthonormal, so we get something like this, where this is the mean of all the faces, that's shown as the first one, and then these are the singular values of everything else. And so we get a lot of negative numbers and positive numbers represented by red and gray, and they all have to be orthonormal. So if we took this image here and we multiplied it by this image and then summed up, it would equal 0. And if we took this image and multiplied it by itself and summed up, it would equal 1. And so that enforces that we learn this type of a factorization, that orthonormality constraint. And then we learn a non-sparse representation of this image in these factors. So we take this color, it represents intensity or value. We take this times this image plus this element here times this image plus this scalar here times this image, and so on. We multiply them all, we add them up, and we get this face. So finally, these are just to give comparisons to what NMF learns. And this is one of the key features of non-negative matrix factorization. If we looked at what the different columns of W look like on this same faces data set, represent those columns of W as images in the same original space, we get something like this. And so notice that each of these images picks out a part of the face. And now we represent this face as a weighted sum of different parts of these faces that we learned from the data set. And so in this case, NMF will often be described as being learning a parts-based representation. Because for faces, we take each face, we take all the faces, and we learn different parts of those faces and represent each face as some linear combination of those parts. If you want to think of topic modeling, we take all of the documents, we learn the different parts of the documents. In this case, those parts would be topics or themes, coherent themes, and then we would represent each document, which would be a column of the matrix X, as a linear combination of those different parts or themes. And so parts-based, when we talk about images, we're thinking about parts-based learning. When we talk about documents, we're thinking about topic-based learning. Really, they all are talking about the same thing if you just think about non-negative matrix factorization. It's taking the data and finding the different aspects of the data that underlie it, and then representing each data point as a sum of those aspects. And we get this, the reason that we can learn something like this with NMF while we don't learn it with SVD is that we have non-negativity constraints. So it's the non-negativity constraints that enforces this parts-based learning.